So love vegetarians. Hello and welcome back to Calculus 1 section 3.2, working with derivatives. So we're going to take a look at the graphical connections between graphs of the function and the graph of the derivative and see which way they work together. By nature, derivative is supposed to describe the function. It's supposed to show certain qualities of the function. So let's connect these now. I'm going to draw a graph that will, on your part, require some OCD in drawing, because in order for it to be the same, you have to do the same thing. So at height 4, I'm going to draw this straight line. Then I'm going to go 45-degree this way. Over here, I'm going to go 2 square up, so at the slope 2. There we go. And then I'm going to go flat again, and I'm going to call this f of x. So in black we have f of x. Now the numbers over here, it's going to cross the x-axis and go, there we go. So this is -5, this is -1, this is 6, and this is 8. So these are important. Now obviously all other numbers are there on x-axis. I just draw the ones where we have some changes happening with the graph. Maybe I can add. Yeah, let's add one more piece. So here, I'm not going to end, I'm going to extend this now. And I'm going to go down. At 13, it's going to just go down. At 19, and it's, let's say it stops there. So that's our f of x. So try to draw the same thing. I did mention day one that you should have square notebooks for this class, but if you don't have them, then just, figure out the best you can. We're going to talk about the way the derivative describes this function. Again, function might show population. You see a population grow, and then population is flat, and then population grows, and population is flat, and then population dies off, and that's done, right? Bacteria, let's say, right? So whatever it is, it could be population, it could be money in the account, hopefully not, right? You start with investing some money, and then it grows, and it's flat, and then you just lose everything, right? It's just, if you gamble on the stock market, it could be like that. So I don't care what this function is for. It's going to be for something. Could be speed, could be whatever. What I'm interested in now is just mechanics of what happens with the derivative. So first off, I'm going to take a look at 2 flat pieces because those are easy. The flat pieces have no change, and derivative will be, what's the derivative if there is no change? Derivatives measure the change. There is no change, the derivative is 0. Very good. So from -1, open circle, to 6, open circle, derivative function is going to be the red line, it's 0. And also between 8 and 13, the derivative is 0. So now the derivative is 0 when f of x is constant. Why? Because there is no change. And that is important to understand. There's no change. If there is no change, well, the derivative that measures change better be 0. Right? Now, let's connect it immediately to something that you see every day. What is your speed when you are at the red light or a stop sign? Is 0. See, there is no change. What kind of change we're talking about? Remember, 60 miles per hour means you go 60 miles forward in 1 hour. If you are standing still, that change in position, let's say Somerville to New York, is 60 miles. And you can drive that in 1 hour if you go 60 miles per hour all the time. So, what changed in time? Your position changed in time because at 1 p.m. you were in Somerville, at 2 p.m. you were in New York, right? So, and that's 1 hour passed, and you went 60 miles forward. Now, if you're parked on the red light, right, the derivative, which is the speed, is a 0. You are not covering the distance in time. It's 0, right? So in time, you stand still. So technically, both of these flat pieces, if you want to talk about the speed, both of the flat pieces would be 0. So what do I have? I have driving, then I have standing still, then I have driving again, standing still, and then driving again, right? Now we're going to take a look at the other lines. So now I have a line over here from -5 to -1. This line has a constant slope of -1. So the derivative between -5 and -1 better be -1. Sorry, +1. Whoa. Hold on, +1. Function is increasing. Now, this would mean, right, if we are, again, you want to talk about speed? Sure, it's 1 mile per hour. You're making a progress, right? Between 6 and 8, it's 2. Because the slope is 2 over 1. You go 2 units up, 1 unit over, 2 units up, 1 unit over. So the constant slope is 2. And now, over here, I just drew whatever, so I actually have to figure out what the slope is for this part. Now, that's very simple. Just count the squares, right? I have 1, 2, 3, 4, 5, 6, 7, 8 in my case. So it goes -8 divided by 6. So that's -4/3. -4/3 would be here. And that's the slope, -4/3. So the red line is f prime of x, it's the derivative. So now what we learned from this graph is that the derivative is 0 when f of x is constant, because there is no change. Now, derivative is, we have 2 more. The derivative is positive when f of x is increasing. And the derivative is negative when f of x is decreasing. So you can look at the graph of the derivative and know immediately that your function is either increasing or decreasing or flat right, and so on. Let me get just going to take a random stock to make sure that I push the right button to shut off the projector. There it is. I put in Home Depot. It doesn't matter, right? Here's the 5-day for Home Depot. Let's do 1 month for Home Depot. This is the way, as you can see, it starts at 185 over there, right? And it ends at 186.85. So we see that there is about $1.50 gain over a month. Now, if you have 10,000 shares, that's $15,000 in a month. I'm not doing anything, right? But you have to own 10,000 shares in order to make that kind of money. So what I want to see here is the trend, right? Now, this is exactly what was happening, but then I want to, with the derivative, I can say, right, the positive slope, the negative slope, positive slope, negative slope, positive slope, all the way up, negative to lose money, positive to gain money, negative to lose money, flat, right? Derivative is 0. I'm not losing, I'm not gaining money. So that's something that it's important, and the derivative will clearly tell us. Now let me see. You would smooth this out, right, as you are doing the analysis. You would smooth this out. So I will smooth this out as a flat, as the increase, as a decrease, as a flat, as the increase. So the derivative is 0. The derivative is positive, meaning I am making money. The derivative is negative. For a very short period of time I lost. And then the derivative over here I said flat again. And then positive again. Why would I want to look at the red line rather than the black line? Red line immediately tells me nothing's happening, winning money, losing money, nothing's happening, winning money, like this. Much faster than if I go and continue it, because when I am looking at the black line, I always have to keep in mind where I start, where I end. So I have to look at two different, right, and try to see, sure, we see it's going up, right? Yeah. But isn't it just easier to just say here, okay, made nothing, made something, lost something, made nothing, made something. It was so much quicker to look at that. So that's the way, so that would be the reason why we would look at the derivative graph for that instance. Now obviously, works with speed, works with pretty much anything else. So now you can go and you can practice this kind of thing. Your exam question could simply be, I print one of these, right, on your exam, and I just say, give me the derivative analysis of this. Right now, obviously, this is exam 3. Right? Because, again, you're not here to learn X's and Y's. No one cares about that, right? Are you actually using this in your economics, engineering, or whatever you guys need, including biology and so on? You want to talk about population, you want to talk about pollution, environment, all of these kind of things, right? If system of any kind is changing, derivative is there to measure it. I don't care what your area of expertise is. I'm giving you a tool that covers all areas of expertise. I can't do them all as examples, so you have to go and you have to say, okay, this is how it applies to my life, right? The things that I'm interested in. Right? So that's that part. Now let's take a look at another graph. Now this one is going to be a little bit different. We are going to have a vertical asymptote on this one. Now this is going to be a little bit more arbitrary than, in terms of drawing. I have to be very precise. I'm going to start like this, and then maybe have a piece like that. So that's my black is f of x. I want to draw on the same xy graph the derivative graph, which will describe what's happening with the original graph. So now what should I do? Well, first off, I'm going to start with what we call horizontal tangency. Why do I want horizontal tangency? Well, at that point, derivative is 0. So I know it's going to cross the x-axis. So the next theoretical piece is that at min-max, derivative is equal to 0. And min-max point, derivative is 0. So that's the next piece that I also want to say, it's also important, is that the vertical asymptote location is always preserved between the derivative and original function. Vertical asymptote location is always preserved. That means that for your derivative, your vertical asymptote is still the same vertical asymptote. And that goes for all of the functions that we will ever work with. Okay, great. So now all I need to do is to fish out the derivative through this. What I have are the two guidelines. I have the dot, right? Because the function, the derivative will have to go through that dot. And anytime you have a min and max situation, you will have that going. And I also have the vertical asymptote, which I am going to also now reinforce in red, because that vertical asymptote needs to be black and red because it serves both functions. What have I learned from before? The derivative is positive when f of x is increasing. Bueno. This part of the function is increasing. We are walking up the hill, right? You read towards the right, and you will see that if you are here, you would be walking up the hill. That means that piece is increasing, and if it's increasing, that means that the derivative is positive. So the derivative should look something like that. Oops. So it should fall into this one and then follow the asymptote down. Does it make sense? Well, the answer is yes, because the second part of this function, which is this part here, is decreasing. Well, you hopefully see also the negative derivative there. That's all from the previous theorem part that we wrote. So, if f of x is increasing, the derivative is negative. If f of x is decreasing, if the derivative is positive, f of x is increasing. If derivative is negative, it's decreasing. There we go. So now if you apply that knowledge to what we have on the graph, you see that the derivative function, which is the red line, has positive y values up to the point. And then it has negative y values, so it's negative, after we go to the right. Now, after the line, this is decreasing function, so it better have all the negative values. Again, because the black part, right, the original function is decreasing, so you better have negative derivative at that point. So now I'm going to connect these. I'm going to color code. So over here, I have the function f of x increasing, and I have the derivative being bigger than 0. Then the next one is in green. F of x is decreasing, and the derivative is less than 0. And the last part is, what other color do I? Orange, I guess. The function f of x is decreasing, the derivative is negative. So those are the three parts. I am always hesitant to actually draw in the dividers. So I'm going to draw dividers for a short period of time and then erase them. So the pink ones would divide the intervals. You have an interval from negative infinity to the maximum value, because that's where the derivative cuts through 0. Derivative will always be positive there. And then you have another one between the two lines, between the two pink lines. That's the decreasing, and after the pink lines, again, function is decreasing, but it's always, again, it's negative than the derivative. So what does the derivative tell us? Derivative tells us that if the function is decreasing, the derivative is negative. If the function is increasing, the derivative is positive. Anytime you have a min and a max on a function, you are going to have the derivative cross the x-axis, and vertical asymptotes are preserved. And now you can draw any function and apply these rules, the ones that I wrote in red. So there are 5 rules, guys. I don't know if you counted these, but let's label them. So 1, 2, 3, 4, and 5. So there are 5 rules there, and if you follow those 5 rules, no matter what I throw at you in terms of a function, you will be able to find the derivative. And now we get to a situation when there is no derivative. So no derivative situation. One example when you have no derivative at a point is any time when you have a spike or a cusp. Let's say you have square root, absolute value of x. Absolute value of x. So y equal absolute value of x will have no derivative at 0. And that's just because of the definition of a function. We know that the derivative is a function, right? We defined that before. Function that generates all slopes. So derivative should be a function. Now, the definition which is on your exam coming up on Thursday, which you have to state the way they was stated, either in a book or what I gave you, that definition is not allowing for 2 different y values at the same x. One x has to have unique y. Now observe what happens here. When I draw the absolute value function, absolute x, and I draw the derivatives, you see that the left-hand side has a decreasing function, therefore -1, and the other one has a +1. Observe that I put open circles. Can I fill them both in? Can I? And the answer is hell no, because the derivative would not be a function. So we say square root of x is not differentiable at x equals 0. Now, clearly, each function has its own, right? Now, do we have the derivative? Yes. Think about the continuity. We talked about it, right? Your function is discontinuous at a certain point, right? For the vertical asymptote or open circle or whatever. It's continuous everywhere else, and we say piecewise continuous. So, is there derivative for absolute x? Yeah, you see the red lines. That's the derivative. However, it's not differentiable at 0. So 1 point is an issue. We're not going to let 1 point ruin it for everything else, right? So what is the derivative of absolute x? Well, it's these two lines, right? But at the same time, the function is not globally differentiable because it's not differentiable at 0. Can I find slopes? Yeah, there are -1 and 1 at all the locations, and then there is no slope. No slope. There's no derivative at 0. Why? Well, because the left side and the right side are both arguing or fighting for their own right. The left side wants that slope to be -1, the right side wants to be +1, and then they do battle, right? So, for us to smooth that out, right, we just say, okay, separate, and there will be no derivative at that point, right? And that's what it is. Now, let's find the derivative of this function. So what I'm going to do now is I'm going to write the pre-calculus definition for absolute value of x. If you remember, it is -x for all x's less than 0, and it's +x for all x's. And see, I can actually put equal if I want to, right? I can assign equal to one of those, and then the derivative will be assigned to that one, but derivative would not exist at that point. Now, the derivative of x is 1. We see the slopes, right? So now if I want to find a y prime, when y prime would be -1 for all x's less than 0 and +1 for all x's bigger than 0. So piecewise functions will have derivatives at each of its pieces separately. Now I have to go back to that big function I had, the second example, and then show, well, I did show earlier, but I want to show one more time, the pieces in there. There it is. It's not differentiable at the vertical asymptote. Vertical asymptote is preserved. So we have the red line derivative in one shot to the left of asymptote, and the one red line derivative in one shot to the right of the line. It's not differentiable at vertical asymptote because you can't compute. Now I want to connect that back to the idea when we had, right, and vertical asymptote preserved talk, when we had that our f of x was 1 over 2x and our f prime of x was -1 over 2x squared. This one will graph this way, and the other one will, red. The derivative will graph this way. Please observe that the vertical asymptote x equals 0 is preserved from the function to the derivative. Preserved. And we also have all other things fall in a place. That's the beauty of mathematics. They always have to fall in a place. I have a decreasing function, I have a negative derivative. I have a decreasing function, I have a negative derivative. The vertical asymptote is at 0, the vertical asymptote is at 0. Right? And not differentiable at 0 because I have vertical asymptote there. So I hope all of this now connects. The book will give you more examples to practice, but that's that. You have to learn those 5 rules and just deal with function not being differentiable if it has a spike or a cusp. Cusp is the one where the slopes tend to go to infinity, right? So this is a spike, the absolute value, right? They come in at an angle and they create a spiky point, right? The cusp actually is more like this, where the top over here is really, really insanely sharp, right? And it actually pokes into infinity. So the slopes from both sides poke to infinity. Now one slope is increasing slope, positive infinity slope. The other one is this from decreasing part, negative infinity, right? So you see the left and the right slopes. We talked over here about, the battle between -1 and +1. For cusps, it's a battle between positive infinity and negative infinity because they are rapidly, right? They're rapidly. So yeah, this is sharp, but this is much sharper, right? That's the graphical representation of those things. Ta-da! I'll see you tomorrow.